How's it going up in Boston, by the way? Are you guys also getting fire from, like, smoke from Canada?
Maybe not. I'm not sure.
No? We're just told it might come back. We're going to be stuck inside again.
Do you mind to pronounce your last name for me?
Of course not. So it's Van Beest.
Okay, no problem.
Marieke Van Beest. Yeah. I know it's not very international.
No,
Actually, even in Denmark, people have problems with it.
it means from somewhere, is it? From the one is from.
Yeah, exactly. That's right. So Beest is an old town in the Netherlands that apparently my family hails from.
How about Beethoven? Van Beethoven is something from somewhere. Van Nomen.
Maybe they're close by. I have no idea. Yeah, it's very common in the Netherlands, right?
Yeah. Okay, I guess we can. Welcome everyone. Welcome TLE. We are very happy to have Marieke Van Beest from Simon Center for Geometry and Physics. She will be speaking about very exciting recent work she did with Philip and Diego, Zoha, and David on the monopole scattering and the generalized symmetries. Please let me remind the audience, please feel free to interact with Marieke and ask questions during her talk. Let's directly welcome Marieke. Please, thank you.
Thank you very much, Ruben. Thanks a lot for the invitation to speak. I've been looking forward to it. And as you say, please do interrupt with questions so that, I can feel there's someone on the other side. I'd much rather be talking to you guys than just, running through slides for however long that'll take. Thank you very much for the nice welcome in my own native language. I'll say good morning to you all as well. Indeed, I'm going to be talking about a recent paper that I have worked on in collaboration with Philip Boyle-Smith and Diego Del Mastro and Zoha Komagotsky and David Tong. And I think 3 out of my 4 collaborators are here, actually. So, right. And indeed, the problem is about monopoles and their scattering and generalized symmetries. Yeah. So I have an extremely simplified outline of the talk right here, but essentially this is what we're going to be doing. So eventually I'm going to want to talk to you guys about monopole scattering. But it turns out that there's a 2D toy model that captures a lot of the essential features of the monopole scattering that's really neat to work with first, just because it doesn't have the complications of any relationship with the gauge theory. And it's sort of really clear what happens in that case. So let's get into it. So the toy model that I want to tell you about is the so-called 3450 model. And that is a 1 + 1D system of free fermions, where I have 2 left-moving fermions that have charges 3 and 4 under some global U1 symmetry, and I have 2 right-moving fermions that have charges 5 and 0. It is a general fact that if you have a theory with an internal symmetry G that has a 't Hooft anomaly, then it can't have a boundary condition preserving the full symmetry G. Therefore, we should, of course, check that this U1 that I've told you that the fermion is charged under is non-anomalous, which it is indeed, because 3 squared plus 4 squared is 5 squared. Also, the theory has no gravitational anomaly because there's 2 left movers and 2 right movers, and that's the main reason for including the uncharged fermion. That's the role it plays. So those are necessary conditions for there to exist a conformal U1 preserving boundary, and you can actually also show explicitly that it does exist, and the people in these references did that. So Philip and David, and also Wang Wen worked on this. So here's the puzzle. Essentially, if I throw the charge 3 fermion at the boundary, it appears that there's no out state that could possibly come out, which is consistent with the existence of this global U1 symmetry. And that's because there's no linear combination of the right movers that I can make that actually has charge 3. They're all going to have charge divisible by 5. Therefore, if I insist on conserving the U1 symmetry, that seems to require that the out state is some kind of fractional excitation. So if I send in the 3, in order for the out state to have charge 3 under this U1 symmetry, I would have to have 3/5 of the charge 5 coming out, and some number of the uncharged fermions. So that's not fixed, and it's not important at this moment. Right, and so the meaning of these fractional particle numbers is not clear and ambiguous at best, and therefore it seems impossible to write down an out state that actually conserves this U1. Now, in order to make progress on this problem, we're going to first consider a slightly more symmetric setup, so a simpler setup. So we're going to consider a boundary state which preserves an additional U1, and that's neat because then you can construct the boundary states explicitly because you have more symmetry. So now I've chosen to label my fermions according to the charges of the first U1 and the U1 prime. We're just going to have to try to remember what the charges are, or you're going to have to believe me that my relatively simple algebra works out. So this is a set of charges under the 2 U1s. And they've been chosen such that there are no 't Hooft anomalies, like no mixed 't Hooft anomaly and no 't Hooft anomaly of each of the individual U1s. And now the scattering is completely fixed by symmetry conservation. And indeed, if I throw in the 3, the only thing that can come out that's consistent with the boundary being symmetric under these U1s is this fractionalized states, where I have 3/5 of the first one and 4/5 of the size 0. Okay, so what to do about these fractional charges? Well, actually, things become slightly more clear if we bosonize these fermions to a theory of free compact bosons instead. So that's by the standard bosonization map. And then we find that we can write the scattering amplitude like this instead. So here I throw in the vertex operator, which it corresponds to the charge 3 fermion. And the thing that comes out is this fractional vertex operator. Now, a fractional vertex operator is going to have correlation functions with branch cuts. And basically, these branch cuts define a symmetry defect in our theory. So in other words, this means that the outgoing radiation is actually attached to a topological line rather than being a local excitation. And the way to see that is if we do pick out some local excitations, we can measure their monodromy around the out state, so around the twist operator, the fractional operator. And we see that it has some non-trivial monodromy. And that non-trivial monodromy measures the action of the topological line that comes out of the scattering. And it turns out that it implements a C5 that's a subgroup of this U1 times U1 prime.
Oh, I have a question.
Yes, please.
So can we, okay, or maybe we cannot, can we write down this topological line or defect in terms of elementary fields of the original 1 + 1D 3450 fermion fields?
The fermion fields, you can write them down, and yeah, that's the point. Actually, the thing that comes out, the topological line, you can write down in terms of the original fermions. It's going to be some current, right? Some linear combination of the fermion number currents that implements the correct symmetry. And then the point is that actually, if we want to write down precisely the out state, we're going to have this line, and the excitations, like the fermions themselves that come out, are going to live in the twisted Hilbert space of this line. So rather than being the original Fock space where the free fermions live, they're going to be in this twisted sector.
Mm-hmm.
Was that what you were thinking, or?
Yes. So far we don't need to include any hypothetical high energy sectors or anything else. Everything is within this 3450 free fermion model.
That's right. It's nice, and that's one of the reasons why why I chose to start with this model, and why we chose to think about it before going into the whole monopole business, is because it's really a very sort of clean scenario. You just have the free fermions to work with. There's nothing like, you don't have a lot of bits and pieces in this theory, right? So you really have to find the answer to what it is that comes out just from your free fermions.
Okay. Thanks.
Yeah, we're not talking about any UV completion or anything. It's really just like this super simple model.
The reason I ask is because sometimes when we have one description of elementary fields, and it's easier to study maybe older parameters or older operators of one type of fields, but maybe the defects of this older operator is hard to analyze from the original theory. So I was to show that we haven't need to introduce any other degree of freedom yet.
No, that's not necessary. Yeah, it's fine. It's just going to be some fractional combination of the fermion number currents.
Okay, thank you very much.
Thank you.
So Marieke, sorry, another question. So maybe this is very like, so how do you compute the monodromy exactly? Is it, I mean, I guess you take the operator and you move it around the thing that comes out.
Exactly.
And how do you see the monodromy?
Well, you just see them. Yeah. So how do you see the monodromy? Well, it comes from looking at the commutation relations of vertex operators, right? And of the free boson, and just using the commutation relations of the bosons, you find that it's non-trivial. That you find some phase, right? So then you get a phase that's like e to the I 2 pi over 5, and that's how we.
All right. Thanks.
Yeah. Cool. Thanks. Any other questions? It's really good that you're asking questions, because this is sort of the point in which I'm trying to convince you guys that this line operator, the appearance of this topological line makes sense, because if you're not buying it now, then you might not buy it later. So, okay, good. So, right. So let's go back to so I took you guys into this little detour of bosonization in order to argue that we have the appearance of a branch cut and of this symmetry defect. But now let's go back to the fermionic language and check that this assertion actually makes sense. And for that to make sense,
let me make sure.
Yeah.
Let me make one more thing. So the Z phi is a common subgroup for the two of U1, U1 prime.
That's right.
Okay, so the group is U1 times U1 prime mod Z5. But this 5, is that something unique about this, or just particular choice of the tool U1? Because you can, you can choose a different way to parameterize torus and different set of U1s. I'm not sure whether the common subgroup might be different. So is that Z phi has something?
Okay, I'm not sure. I'm not sure exactly what you mean. So are you saying if I wrote down a model that's almost like this one, but I picked some different U1s, like with different charges for the fermions? Yeah. Well, let's see. So I think it's going to be a general feature that it's there. The thing is, so I'm going to talk in a little bit more generality what happens if I just have a single U1, and if we can still be, because then, it's a common subgroup. It doesn't just sit inside one of them. I'm going to talk about that in a minute, that we can still be sure that this line operator exists. If you just pick the completely different set of charges where you can still create this paradox. I haven't checked explicitly, but I think there's still going to be something like this. And I can see that, was that I don't know. Yeah, I haven't checked for like many different types of these charges. The 3450 model was chosen because it has this paradox built into it, and we checked also in the case where we don't have the 2U1s, and I'm going to get into that. But if I just had a completely different set of charges, I mean, it might not be a Z5. It's probably going to be some other subgroup.
Mm-hmm.
I see also there's a message in the chat. Was the symmetric boundary actually constructed, or is it an assumption that one exists? You can actually construct the boundary state explicitly. And also in our paper, there's a derivation of this. Sure. And then I see that Maxime has raised her hand. Please.
Quick question. Are you going to explain like how you set up this scattering? I mean, are you going to build up like a wave packet and then, or you're not?
For the monopole? For the monopole scattering?
No, even in this simple 1 + 1D.
Like here? I mean, I don't know. I mean, the short answer is no. I mean, it's just free fermions, and some set can go to the left, some set can go to the right, and then there's this boundary state that connects them in some non-trivial fashion, right? That has some boundary state that turns them into one another in some non-trivial fashion. I don't think I'm going to unwrap that structure much more.
I mean, is the outgoing state, should I think of it as like a wave packet which is dragging a branch cut behind it? And it's a little confusing.
Yeah. Okay. So the outgoing state you should think about as a local excitation. Tracing out a line operator behind it. So I have a left moving fermion that hits the boundary, and out comes something like a local excitation that moves to the right, and behind it trails this topological operator. So that's the way, to think about it.
Okay.
Thank you. Okay. Any more questions? Otherwise, we'll get back to the fermion language. So now we're going to compute the yes.
One more, just make sure. But the title is about monopole, scattering with monopole. But here you are scattered with this symmetry gap. Maybe we'll also call the symmetry mass generation for the 3450 model. Is it? So these two things may not be the same at this moment, at least for now, right? The one is the monopole.
Yeah, they're not going to be the same. No.
Right, you are doing the symmetry gap on one side. Is that right?
Yeah.
Okay, so we haven't got monopole yet, right?
We haven't gotten to the monopoles yet. No. So right now I'm just talking about a much simpler scenario, and they're going to be related. But as you correctly point out, like there's going to be several extra features and subtleties for the monopole, and that we're going to add on to it. But it will have. I promise you, it will have a relevance, which is why I'm going for it. It will be very similar.
And Halda has a question.
Oh yeah, it's a question related to Max's questions before. So you mentioned these pictures where you have the wave packets and a line attached to it, but that's a picture at the fixed time slice, right? So if I think of it in space-time, then that line seems to trace out a world sheet rather than just having a topological line. So
yeah. Right. Let's see. So the topological line, it is actually a world line. It's traced out by the fermion. So I'd say in Euclidean space, like it's a line operator, but if you're thinking about the Minkowski picture, then it's a world line.
It's okay. So it's just a world line. So I see. Okay. Yeah. Thanks.
Okay. So let's check that that the line operator actually does the thing like that we set out to do, which is it gives us an outgoing state where these U1s are conserved. So we'll call the generator of the C5, we'll call that T. And by doing this monotony computation, we can see that the left-moving fermions aren't charged under it at all. It only acts on the right movers, and the right movers have, and that's just because the left and right moving the left and right moving bosonic fields, they just commute. So you don't get a monotony. So they act on the right movers, and they have charges 3 and 4 mod 5. And once you know the charges and we know everything about this U1 times U1 prime, then you can sit down and you can compute the charge of the line operator with the excitation at the end, right? So the thing that comes out is a topological line with a fermion excitation at the end. And of course, the fermion excitation is just going to carry the global quantum numbers of, like, it just carries the whatever global quantum numbers it carried before, whether or not it lives at the end of the line or just lives by itself in the usual fermion Fock space. But the topological line itself, the vacuum in this twisted sector, actually carries charges as well. So these are the ones that we're going to compute. And if you do that, you can compute it for T to some power K, where K runs from 0 to 4. And you see that you find these charges. And the fact that you compute these charges actually completely fixes the outgoing state, so that it has to be psi 3 scattering to just this topological line to the first power with a 5 and a 0 charge right-moving fermion living at the end. So this, just to be completely clear, this notation that we have here on the right-hand side, we write the line plus some excitation, is shorthand for write down the twisted Hilbert space and create fermion excitations on top of that vacuum, not in the untwisted sector. So this is the shorthand for that. Right, so looking at these vacuum charges, it's simple to check that indeed we have preservation of this U1 times U1 prime, and the way it's preserved is that the vacuum of the twisted Hilbert space itself is carrying charges -2 and 1 under this U1 times U1 prime, whereas the outgoing state carries 5, 0, and 0, 5, and we find that it is conserved. So where did the fractionalization go? Are these states still fractional in any sense? Because now, instead of having these funny 3/5 of a fermion, I just have a line operator and a perfectly integral excitation in that Fock space, in that Hilbert space. So where did the fractional stuff go? Well, basically, if we do sit down and measure the particle number of the outstate, so the whole line plus the excitation at the end, say I want to measure the charge associated to this current of the charge 5 fermion, I will get a fractional number. I will get a fractional charge. And the reason it's fractional is because the bulk symmetry has a mixed Tooft anomaly with this C5. So that the fermion number has a mixed Tooft anomaly with this C5, so that the vacuum at the endpoint adds fractional charge. So if I do sit down and measure the fermion numbers, I still get these fractionalized states, but the correct interpretation is not, oh, I have some fractional occupation number in my usual Hilbert space. Rather, I need to go to this twisted sector. Okay, and now going back to Yuvin's question. So now we've considered the U1 times U1 prime symmetric boundary, and we found a consistent outstate. But I started out by phrasing this puzzle just for a single U1. And indeed, it arises already for the symmetric boundary states. So we have to figure those out as well, obviously, because that's where the paradox starts. So if we consider a boundary state preserving only a single U1, we're not a priori guaranteed the existence of this crucial C5 symmetry. And if I don't have the C5 symmetry, because that was a subgroup of U1 times U1 prime, if it turns out I don't have it or anything like it for just a single U1, then this is not going to work, right? Then I don't have a topological line. But this question can be settled by explicitly constructing the boundary states. And one thing that's good to keep in mind also for the monopole case is that in general, say I have n direct fermions that enjoy a symmetry G that sits inside their flavor symmetry SON, then that is going to have a unique symmetric boundary condition if the rank of the symmetry is equal to the number of direct fermions. Right, so that's what's happening in the U1 times U1 prime case. So there I have two U1s, and I have two left moving to right moving states, so that the symmetric boundary condition is that's completely fixed, and you can write it down. However, it turns out that even if I have that the rank of the symmetry of my theory is one smaller than the number of fermions, we can actually still classify the Carty states thanks to conformal invariance. So that's the single U1 case here for the 3450 model. So you can write down this classification, and once you do that, it actually turns out that having a single U1, like having the boundary state be symmetric under a single U1, automatically implies that it's U1 times U1 prime symmetric. Like you can't write down a boundary state that only has a single U1 except for a few pathological cases, but everything physical is actually going to have the full U1 times U1 prime. So we always have the C5 subgroup, and this resolution of the problem always works. Okay, so any more questions about this simple toy model? Otherwise, I'm going to move on to the monopole case, and you'll get some idea like why I took you through this simplified case and what it has to do with the monopole.
I think BR has a question. Maybe.
Oh yes, please.
BR. I'm not sure who is BR.
In the chat?
Yes, in the chat, but
Hi, sorry, it's Brandon. I don't know why my phone abbreviates me to BR, but I was just wondering if you meant SO2N, that's all.
If I mean SO2, oh, SO2N. No, I don't think I mean SO2N. So the reason why is because I mean, this is the subgroup of the full flavor symmetry, right? But the reason why is because the full flavor symmetry always has a 't Hooft anomaly. So we're never going to be able to preserve the full one.
Gotcha, thanks.
Thank you.
I think this question may not be intelligent, but let me ask it anyway. What's special about this 5 again? Is that just because maybe some Pythagoras rule give the top a squared plus b squared equals c squared, the c will be the 5. So that's the reason for that.
Sorry, so what's special about this model?
It's 5. No, for the 5, not for the model. I certainly know this model well enough.
Yeah, I know. I was just wondering in this context.
I don't know why this the Z5 is important.
Oh, the symmetry. Yeah, sorry. Yeah.
Because I just think that you can certainly choose, 2U1, which does not have an overlapping discrete subgroup. But I'm sure the physics should be the same, right? So that's not. So the Z5 may have some meaning here, maybe some simple, but I don't see how should I state that. For
so
example,
I think
I change like to left moving to right moving fermion, all of them have some charge. Nothing has like zero charge like a neutrino. If some all of them don't have some charge, then maybe this number will be interpreted.
I think this is what you're getting at. So there's some part of this U1 times U1 prime that doesn't act faithfully on the fermions. Yeah, and I'm not sure we wrote that down anywhere actually, but this C5 is related to the fact that it doesn't act faithfully. So it's yeah. And so if you sorry.
But I think maybe you say something about the anomaly, mixed anomaly with Z5. Can you state that again? The Z, what's that?
So that was a statement about fermion number, species number currents. If I take the fermion number currents, like this for the psi5, then they're going to have a 't Hooft anomaly with the C5, which is why when I try to measure the charge of the full state and like the fermion number of the full state, it's going to be fractional.
Okay.
That's all I was saying there. Yeah.
Okay. Oh, I think Ofri Tellem. Please go ahead, Ofri.
Hi.
Hello.
Some questions. So if I'm a 2D experimentalist sitting there with a detector and I detect something with the right fractional charge, did I actually detect a new state in my theory that I didn't know exists, and that was my mistake? Or did I now detect like a clutch of my original fields in some non-linear fractional combination?
Mm.
That was my mistake.
Yeah. Okay. So if you're thinking something similar to Eugen, like, do I need to introduce some new degrees of freedom? The answer is no. You don't need to introduce new degrees of freedom. You just have your free fermions, and everything I've said so far, you can build it out of the free fermions. The thing you've added is, well, you haven't added it, so to speak. That was wrong. The thing that we have in the scattering experiment that we weren't thinking about before is we have the appearance of this topological line. So the topological line is, so to speak, an intrinsic part of the theory. Because of the existence of the global symmetries, this thing exists. But the fact that it comes out of the scattering experiment is the new thing. And you could say, if you were an experimentalist and you sit down and measure the outstate of this experiment, you're just going to measure some fractional charges, right? If you actually wanted to convince yourself that there is a line, you would have to, and I don't know how to design this, but you would have to figure out a way to design an experiment where you pick up this monodromy, right? So you'd have to somehow cross the line and see that it acts on the free fermions. That would be the way to convince yourself that there's a distinction between what I'm saying with the topological line and just measuring fractional electrons, so to speak, or fermions. Yeah.
All right, thank you.
Thanks. Okay.
Actually, just make sure. I think in the end of the scattering, you give a process of the charge 3 fermion incoming and outgoing with this topological line.
Yeah.
Plus charge 5 and charge 0 the outgoing fermion, right? And
yeah.
But the dimensionality for this the T topological line is not point object. It's one dimension, right?
It's a world line. Yeah. So from a Euclidean point of view, it's a line operator.
Right, but usually when we say this U1 and U1 prime symmetry, this is still a zero dimension, zero symmetry, zero form symmetry.
Yes.
Whether this charge object usually is 0 dimension, while the symmetry generator or charge operator is codimension. This is one dimension, codimension 1 in 2D, right?
Mm-hmm.
And then but then the topological line T seems not obey the usual way to think about the charge object. At least the dimensionality is different. Is there some?
Is it?
Understanding?
So I'm usually, so when I do this, zero form symmetry corresponding to a D minus, or a P form symmetry corresponding to a D minus P minus 1 form, D minus P minus 1 dimensional symmetry operator, I'm usually in Euclidean space. So I think then it works out, right? The thing that's a little bit funny about this one is that it actually extends along the time direction also, right? So I think the dimensionality works out. If I have, so this is let's say it's a Euclidean 2D model, then I have a zero form symmetry corresponding to a 2 minus 0 minus 1 dimensional symmetry defect. Works out to a one-dimensional line. And then the thing that's a little different here is that we actually in the end want to go back to something that's Lorentzian, and then it turns out to be a world line. But I think the dimensionality works out.
So what is attached is the symmetry operator, right? Not the charged operator. I think this is the.
Yeah. Oh, okay. I'm sorry. Yes. Thank you. So the thing that's right. So the excitation that comes out trails behind it a line, and the line it trails behind it is a symmetry generator. So it's it's the generator of the symmetry. It's not the charged object. The charged objects are indeed the local fermions.
Yes, but you still assign the, sorry, the T is the Z5 symmetry generator, is it? Which is one dimension. But you still assign the U1 prime charge to T.
It is the endpoint of the line that carries charge.
Right. Yeah, that's the point I was asking. Yeah. Okay. If that's the case, I think I get it.
Thank you, Diego. I wasn't getting it.
Yeah. Okay. Yeah. Even though the line is symmetry generator, the Z5 is 1D, but the endpoint of that still carries on U1 and U1 prime charge.
Exactly. Yeah.
Okay, then that's fine because that's a 0D object which can be charged under the zero form symmetry of U1 and U1 prime, which is okay.
Now I see what you were getting at. Yeah. Okay. And thanks, Diego. Okay. Now, the whole reason I've been telling you about this simple free fermions model is that an analogous story happens to arise with the scattering of massless fermions of magnetic monopoles in 3+1D U1 gauge theory. So with magnetic monopoles, we think of as Twift lines in this effective field theory approach. And that was actually something that Kallen and Rubakov discovered already in the 80s for the first time, where they made the rather confusing observation that even though the in-states are perfectly standard wave packets of charged particles, then the outgoing states can actually have fractional quantum numbers. So I'm first going to work at tree level, meaning that I'm going to take the gauge field to just be background with n units of flux through the transverse sphere, so the sphere surrounding the monopole. And I'm not going to take into consideration gauge fluctuations yet. We'll get to that a little bit later. And then I'm going to consider a charge Q fermion in this background and wonder about what happens if I throw this fermion at the monopole and ask what comes out. So classically, if I analyze this problem, charged particles are just repelled from magnetic monopoles, right? They just like a comet, they come in, they scatter off, and they go out again. But quantum mechanically, it turns out when you solve the Dirac equation that the lowest angular momentum mode can actually penetrate this barrier. So it can reach the core of the monopole and it can interact with the UV degrees of freedom that are trapped there. And when I say, so in the case of a unit charge monopole that is most familiar to everyone, and a unit charge fermion like in QED, then the lowest angular momentum mode is just going to be the S wave, right? So it's just going to be the spherical moment, the spherical mode that collapses on the monopole. But if you have a higher charge monopole, it's not necessarily going to be the S wave that's the lowest lying angular momentum mode, but you can have higher modes in the spherical harmonics. So it turns out that once you solve the Dirac equation, you'll see that the dynamics of this lowest lying angular momentum mode effectively reduces to a theory of 2D massless free fermions with a boundary. And this is the reason I was telling you about the 3450 model. So in the tree level approximation, the 2D model is not going to have any gauge fluctuations. So we're just getting free fermions again. And the reduction is such that for every like that the chirality and the infalling outgoing motion is correlated, importantly, for this lowest lying mode. So if I have a left-handed chiral fermion, then that's going to reduce to n times q left-moving fermions in the 2D theory, whereas the right-handed ones are going to reduce to right movers. So we have them separated in infalling and outgoing motion, and the monopole itself is just going to be modeled by some boundary condition. Right. So one thing that we're going to require of this boundary is that it preserves the electric U1 or U1 gauge, as we call it. And for that to be possible, the 2D gravitational anomaly has to vanish, and U1 gauge can't have any anomalies as well. And the equations in equations that with those requirements look like this. And it's relatively simple to show that if this holds for the 4D theories, this holds if the 4D theory has no anomalies, right? So if the 4D theory is a consistent theory with no gauge gravitational anomaly and no gauge anomalies, then the boundary is automatically going to preserve U1 gauge, and it's not going to have a gravitational anomaly in 2D. Yes, that's another question.
Sorry, why is it U1 squared? U1 gauge squared?
Yeah, so what I mean by that is just we use the notation where if I had several U1s, I'd say like U1 times U1, U1 prime can have a mixed anomaly. So I just use the notation to say that it's just an intrinsic anomaly of U1 gauge rather than something mixed.
It's 1 plus 1D 2-point function with 2 probe field, just the triangle diagram is 3 plus 1. These are 1 plus 1.
What is the second? I understand there is an overall U1 conservation, which is also related to the to the monopole. What is the other U1 symmetry?
Oh, sorry, that was probably a confusing comment. I was referring back to the 3450 model. There's no other U1.
Okay.
Yeah, sorry about that.
But then why are there two conditions for?
So the first condition is just that there's no gravitational anomaly. So that condition is just that the central charges of the left and right movers that they match.
Yes.
Or that, yeah. So that's my first condition, and then my second condition is that I want the boundary to preserve this U1 gauge, the U1 that descends from the gauge symmetry in 4D. And for that to be possible at all, the U1 gauge can't have a 't Hooft anomaly in 2D. So I need to check. I'm just checking that is even possible.
Why is there there is NQI sum equals 0 and NQI cubed sum equal to 0?
Right. So those correspond to respectively a 2D gravitational anomaly and a U1 gauge anomaly.
Okay.
So the reason you get these extra factors of Q and N is it's just coming from the sum. It's the fact that each of these fermions in 4D reduce not to a single left mover, but to N times Q left movers or right movers respectively. So that's why instead of having Q squared here like we're used to, once you reduce on a sphere with N units of flux over it, you get these extra factors. But at the end of the day, all I'm saying is just that they're going to be satisfied if Q squared they're going to be satisfied if the 4D theory is consistent.
Good. Thank you so much.
Thank you. Okay, so let's start by thinking about the unit charge monopole. And the reason we start by doing that is, again, because here we have enough symmetry to write down an explicit boundary condition. So that's the point I was making before, that if I have a lot more degrees of freedom than I have global symmetries, then you completely lose control over what the boundary state is. So in this case, if we just take the unit charge monopole, then we don't get as many degrees of freedom in 2D, and we can actually write down an explicit boundary condition. Now, the usual QAD, which arises from simple UV completions, say you can write down the SU2 Georgi Glashow model, and that's going to give rise to these representations. Has the following charges, so plus minus 1 under the U1 gauge, and they live in the same representation of the flavor symmetry. And here comes the problem. So again, if I try to just throw in some psi, it appears that there's no obvious candidate for the outstate which can preserve these symmetries, which preserve both the U1 gauge as well as the flavor symmetry. So say I try to say, okay, I throw in a psi, then out comes the corresponding right mover, right? That's not going to be right because it doesn't conserve electric charge, and we want the monopole scattering to, or we know that the monopole scattering should conserve electric charge. So the other obvious guess would be, okay, the thing that comes out is psi tilde dagger, but then that breaks the flavor symmetry. So it seems like we can't write anything down. On the other hand, we can do abelian bosonization in this case, so that's only going to capture what the carton is doing. So when I go from the fermion description and then going to bosons using abelian bosonization, I'm only capturing the carton. But if we just focus on that, then we actually have an explicit boundary condition that's well known from the literature, and it's known to produce these fractionalized outstates. So in the bosonic language, the thing that comes out, if I throw in the ith vertex operator, is this fractional state on the right-hand side. And just to convince you guys that I'm not making this stuff up, indeed, these are precisely the fractional particles that were found by Kellen in '83, where he comments that it's a simple matter to write down the outgoing state. The final state is a collection of half solitons. And in particle language, we have these factors of a half in front of the electrons and the quarks. And as he says, although strange, the answer is quite definite, and we must decide how to interpret it. And people have been trying to interpret this ever since this paper came out. So now the analogy with the 3450 model is clear, right? So we throw in something like some perfectly good fermion, and out comes something fractional. So instead of
sorry,
yes,
just
yeah.
What's the factor of 1/2 again? The 2. Why is the 2? Maybe I missed some part.
Yeah, we're here.
What's the 2?
Sorry, where?
Why there is a factor of 2, 1/2 in front of those quarks and U quark, D quark, and the electrons?
Oh, here, yeah. So he's taking some specific number of. So he's taking presumably a unit charge monopole first of all, and then it appears he's taking four fermions. Yeah, then it works out. Then you get a factor of a half.
Okay, but is there some like a simple way to state that why is that factor 2? I think my question is always so naive. I think I was at the factor 5 and now it's factor 2. I think there should be some simple way to state it, but I don't hear that statement.
No, actually, no, you're certainly excused. These things are kind of important, right? When you're talking about C5 symmetries or something, it's important that if there's a factor of 2, you're doing something completely different. Yeah, so but this factor of 1/2 that Kellen had in his paper, it's not like a fixed factor of 1/2. Really, what he's got there is 1 over the fermion number, so 1 over NF, and he's taken some particular choice, like he's picked the QED with some number of fermions.
Okay.
So the real answer is at the bottom here. It depends on the fermion number.
So this is not exactly certain standard model in his calculation, but he has quarks and leptons. But it's not the standard model quantum number give rise to this 1/2.
Oh, right. No, I think it's, yeah. Okay, so it's not quite as simple as what I was saying, but I think he's picked okay, I can't honestly remember exactly what the field constant is, but I think you're right, it's probably the standard model, right? So he picked the standard model, and then this factor of 1/2 comes from this field constant in some way that I can't right now write down for you. I'm not sure, but it has to be yeah, the contributions from all the different fermions in his theory, and that turns out to be a factor of 1/2.
Sure. Okay, that's fine. Thank you.
Yeah, we didn't do the standard model in the end. That's because there's an additional complication. We can discuss that at the end, possibly. Okay. So the next thing I want to say is, of course, instead of associating this state with fractional occupation numbers for free fermions, we want to interpret it as the appearance of a topological line again. So here we're going to let T be the generator of a ZNF. And this CNF is just the center of the flavor symmetry up to a gauge transformation. And then you can write down the quantum numbers, and you can check that the thing that comes out, which preserves all the symmetries, is actually this line to the -2, and just the corresponding right mover living at the end. And this scattering state is has a perfectly integral interpretation in this twisted Fock space, and it preserves all the symmetries of the problem. So the really interesting case, though, is higher charge monopoles. So when I make the charge of the monopole larger than 1, the topological line that trails the out state are no longer just C and F, but it's C N and F, where N is the charge of the monopole. And it's the axial, it acts as the axial symmetry. So the generator T of this set N and F acts on the fermions like this.
Makes
Yeah.
I'm going to talk about how to interpret this line in 3+1D. Like
yeah.
Okay, thank you.
It's yeah, you're anticipating basically my next slide, I think.
Okay, thank you.
Yeah. But to finish up with 2D, this is some axial symmetry lines, some discrete subgroup of the axial symmetry that is invertible and non-anomalous in 2D, and it comes out and it preserves all the symmetries of the problem. And now, yeah, the question is of uplifting to 3+1D. So, and that's why we wanted to talk about the higher charge monopoles, actually. So the uplift of this picture to 40 leads to a new prediction in the sense that we find an outgoing wave that is trailed by a 3D surface with a fractional quantum Hall state living on it. So if you look at the action of the line on the fermions in 2D and uplift this to 40 such that like it matches the action on the fermions, it determines the surface to be none other than the non-vertible axial symmetry defect that Shuheng and Yichul and Hotat, as well as Kodora and Omori found recently. So just in case not everybody is familiar with this work, so in QED, the axial symmetry suffers from an APJ anomaly, which looks like this. And due to that anomaly, then the usual symmetry operator that we would write down that implements the axial symmetry is not topological. But these people identified recently a discrete topological and Gauge invariant operator that, well, an improvement of this axial symmetry operator that is both a topological and Gauge invariant, which looks like this, where this A and P is the minimal TQ of T with one form symmetry set N and an anomaly which is labeled by P. And this notation with the brackets refers to coupling of refers to coupling to a background 2 form for the one form symmetry. And in this case, this background 2 form is just the field strength of the electromagnetic field in the bulk, right? So that's what these people wrote down. And in case you're not familiar with this TQ of T, it has a Chern-Simons description. For P + 1, it's very simple to write down. I'm sure everybody will be familiar with this sort of TQ of T. And the presence of this TQ of T on the surface results in non-invertible fusion. So if you try to compute the fusion of two surfaces like this with one another, because it's a TQ of T, it turns out that the symmetry defect is in fact non-invertible. Then the 2D invertible topological line that we found in the outgoing state actually uplifts to this non-invertible defect, where this P over N label is 2 over the charge of the monopole. And indeed, when the charge of the monopole is higher than 2, the symmetry operator is non-invertible. Whereas if you have a unit charge monopole, it's just the invertible, it's an invertible subgroup of the axial symmetry. Finally, I haven't told you in 3D how the defect accounts for the missing charge, right? So our whole problem was I throw in a +1 charge fermion, and I don't have anything that can come out. That's a local excitation that preserves this symmetry, as well as the flavor symmetry. But now I found this defect, so how does that account for the missing charge? Well, for even n, it's very easy to, it works, you can do it for n odd as well. It's just to have some slightly shorter equations. For even n, the partition function on the defect looks like this. You just have this quantum Hall state. And because the monopole creates flux through the sphere, Oh, sorry, this is a typo. This shouldn't have been gamma. This should have been over the whole space. Gamma is just a world line. What we find, well, we can just integrate out this flux. We find this world line, and this has a very simple interpretation. This partition function has a simple interpretation as the expectation value of the anyon W to the n smeared over the sphere, where W is just this Wilson line. So it's the generating line. Well, no, sorry. Well, W is the generating line of the Z n halves one-form symmetry. So what does that mean? That means that the surface that comes out in the scattering experiment carries a Wilson line with it. The Wilson line is smeared over the S2. And the Wilson line, because it's this W to the little n, is transparent in the TQFT. So it doesn't give rise to any anion excitation in the TQFT itself. But under the electromagnetic symmetry, it actually carries charge +2. Which precisely accounts for the discrepancy in charge between the incoming state and the outgoing excitation and the excitation living at the end of this surface. Okay, so this is the picture, and just to be clear, because I think this is a common question. So imagine just taking the charge 1 monopole, right, and just charge 1 electric charge 1 fermions. Then the lowest lying mode, which scatters non-trivial, the lowest lying angular momentum mode of the fermions, which is the thing that scatters non-trivially with monopole. For all the higher modes, they just are deflected. That's the S wave. So we have a spherical shell, which collapses on the monopole. The spherical shell interacts. The rest of the higher modes don't interact. And then it comes out trailing the surface. So you have to imagine a spherical shell. And then adding in the time direction, you find this 3D operator that carries the quantum Hall state on it. So this is the picture. Any questions about this? Okay. Yes.
Maybe I'll ask a question. So this surface, does it need to kind of terminate on a monopole, or
yes,
you can have it, you can have it like in just if you think about the defect itself, can it terminate not on a monopole? Is that allowed?
Oh, so in the scattering experiment, it has to end topologically on the monopole, and you can see that already in 2D because you have this conformal boundary. You don't want to deposit any energy on it, so therefore the junction has to be topological. But I think so. What you're asking is that could I in principle have this defect operator exist outside of the context of being attached to a monopole?
That's
what
true.
you're asking? Yeah. So I think in principle, yes. But this is the only way I know of in which to create it dynamically in an experiment. So if I have just QED, I can put it in by hand. I can say, okay, I have this. I want to ask about the action of this operator on certain like on the fermions, and I can put it into my theory. But if you wanted to appear dynamically in some experiment, this is the way we know how to do it.
I see. And I didn't quite understand the comment about the Wilson line. If you maybe go back.
Yeah, so the comment about the Wilson line is just in 2D, I could sit down and compute the quantum numbers of the outgoing state. I could compute the charge of the endpoint of the line under the U1 gauge, and I could find that it indeed accounts for the missing, like the discrepancy of charge between the incoming state and the excitation that lives at the end of the line. So in 4D, I've just told you that I throw in a fermion which has charge +1 under the electric. Well, it has +1 electric charge, and then the thing that comes out is some surface and an excitation that lives at the end of it, which has -1 electric charge. So we need +2 electric charge coming from somewhere. And then the question is, where is that coming from? Like, how is the defect accounting for the missing charge? And then I'm just saying, if you write down the partition function on the defect, and we're just using that we know that the monopole sits there in the middle, because it sits there in the middle, you have this flux over the sphere. And this extremely primitive computation then can be interpreted as just having a Chern-Simons theory here on the right-hand side, just have a Chern-Simons theory with the insertion of a line operator. So you just have the insertion of a line operator in the path integral. And this is a transparent Wilson line in the TQ of T. But if you compute the charge under the bulk electromagnetic symmetry, it turns out to have charge 1.
And what is gamma?
Yeah, so that was, as I was saying, I actually have a typo. So it shouldn't be gamma in the first one. So in the first one, it should be over the entire surface. And gamma here is supposed to be the world line.
But it can be any, gamma can be any line from the monopole to the surface, to the end of the surface, or?
So gamma is a line that stretches in the radial and the time directions, right? So essentially you can think of gamma as the direction of this line in 2D, right? And then you have to add in the sphere, and it's smeared over the sphere.
I thought everything is at a fixed time slice, no?
No. So when I show a diagram like this, I'm suppressing of course suppressing an angular direction, but this is actually a space-time diagram.
So the Chern-Simons theory lives on what space?
So the Chern-Simons theory also extends in the time direction.
But it's a 3-dimensional. So
yeah, it's a Euclidean 3-dimensional thing, and it includes it has a non-trivial component at long time.
Okay, thank you.
Eugen?
Yes.
Or
yeah. Let me just make sure many things. Yeah, I think it's also related to Max's question.
Yeah.
First of all, monopole is a point in the space, but do you regard
Yes.
it as a whole line or in space-time? Is it a 1D line or a point? Or
So
should
we're
I
thinking of
think the end of a tunnel?
yeah. So indeed, so we want to consider a heavy monopole. So we're just thinking about it as a 't line. So the well, so it's a local. What, how do you say it? Well, in a Lorentzian picture, it's a local operator, right? It's a local operator, and that has a world line. The world line traces out the 't line, and that's the thing I'm scattering against.
Yes, and then you put that line along the time direction, so you only see a point in the space.
Yes.
And then this picture fermion scatter and incoming is a point particle, but it also has some line directions, and then there's an outgoing line as well, and these are point particle in the space. But I think the next question is that then how should one think about this quantum Hall states? Is everywhere in the light cone, or nearly a light cone? If it's massless, then it would be a light cone, but I don't know. It's massless, right? Massless.
Yes, they're massless. Yeah, they're massless.
So this will span the light cone in 3D.
Yes.
You attach a 3D to a light cone, and light cone of course include two space, some space coordinate, 2 space and 1 time in order to be 3D in the space time. Okay.
That's the picture.
Okay, great. But then when you reinterpret the 3D fractional quantum Hall in terms of the Wilson line, well, that line will be arbitrary line that you need to do the path integral summation in every possible direction in the light ray, right?
Yeah, in every part. So exactly. So that's what I meant when I was saying it's smeared along the S2. So it's I mean, it is a line, but you have to consider it being smeared in this angular direction.
Every possible direction on the light cone, I think.
Yes.
Oh, actually, because that line can be it can also be arbitrary along the line cone, is it right? It doesn't.
Yeah, so it's topological, so I can move it around at no cost.
You need to integrate over all this 3D surface in the space-time, which is the light cone. And but however, the outgoing psi r is just one direction possible, constrained by the kinematics of the incoming direction of the psi l, and you can compute the psi r, which will just be some direction. But regardless where the psi l coming from and psi r coming out, you still need to consider the fractional quantum hole over all possible directions on the light cone.
Yeah.
Okay.
Yes. And so I think what we're pointing to here is also, I mean, of course, we're viewing these incoming electrons as they're particles, right? So they're going to be localized in space. So the reason why we end up with this spherical behavior is because it's at this level, at this order in the coupling constant, so like at tree level, you actually only have the interaction with the lowest lying momentum mode. So the thing is, it's true that the thing I throw in is just an electron, you know, it sits somewhere in space, and the thing that comes out is an electron that sits somewhere in space. But at this level of the analysis, we actually only have an interaction of the monopole with a single one of the angular momentum modes. And that's why it comes out attached to that, so to speak. And this conclusion is going to be modified at higher orders.
I think I can follow up on Matt Reese's question. Matt, please.
Yeah, I have a couple of questions that I think are related, but I guess let me start by asking something that I think is related to several other questions that have come up, but I'm still a little confused about it, which is you've talked about this as an operator. I guess I'm confused about sort of operators versus states. You know, if I think about something like a Wilson line, I can think of it as an operator that I can act with at fixed time and create some sort of state. Or I can think of it as like a defect, that's some sort of like static object that I can probe my theory with. Here you're talking about this symmetry operator, which I think of as some codimension 1 operator in the Euclidean theory. But now you have this Minkowski's picture of the scattering experiment you can do. And you've sort of described this 3D operator as being like the surface of a sphere that also has a time direction that's expanding out, right?
Mm-hmm.
But it's not a defect because it's like an actual dynamical state I can produce in my theory. It's not like a static probe that we put in by hand. And I guess that's what confuses me. Usually when I think about sort of trading operators for things that are time-like, I think of trading them for defects that I can put in, you know, as a probe, but that I can't actually make in an experiment. So I'm a little confused about how to think about this. Can you clarify it?
Yeah, I understand. I understand the confusion. Let me see what I can say. Well, okay, maybe I'm not sure how much this clears it up, but the thing is, I mean, the defect itself is also topological, right? So saying that it extends in some direction in space-time is, well, not really a unique statement. So I suppose we could deform it in some way in order to put it in a time slice so that we're more comfortable with them.
I'm not sure if that totally cleared it up for me, but
yeah, no, I know.
Is
So
there
honestly,
like
I think it's a very good
surface?
question, and yeah, I think I might have to honestly think more about it before I can give a very clear answer. Yeah.
Okay, well,
Please
let
continue.
me ask another question that I guess is sort of related, I think. Is your picture of this compatible with, I don't know if you're familiar, there was this paper by Hamada and collaborators a year or two back, right? Where they basically said they talked in the language of the Dion collective coordinate on the monopole world line, which is something I'm more familiar with. And their picture was basically that in these scattering events, that Dion coordinate sort of moves part of the way around the circle, and that effectively shifts the Fock space of the states, right? So it's almost like some kind of discrete theta angle or something that changes what the allowed charges in the theory are. Is your picture compatible with that picture?
I believe it is. So this switch or this shift in the Fock space, I think they even make this comment themselves that it can be interpreted as a twisted sector. So I believe that those two are the different perspectives on the same thing.
Good. Okay. So in that viewpoint, you have the scattering event. It comes in sort of localized on the monopole. There's this degree of freedom that gets sort of virtually excited, and it stops moving. So you don't give charge to the monopole. You don't deposit charge on the monopole, but you do sort of shift the state of the monopole in some way that changes the Fock space. And in that picture, I guess you would expect that after the scattering event, there's sort of this outgoing light cone that sort of carries the news that the monopole state is not what it was before, right? And that's kind of what your surface is.
Yeah, I suppose you could say that, right? In the sense that the surface is attached to the monopole at the other end. So you're saying that we could instead think of this as a property of the monopole, that it has somehow changed its state. Is that correct? Is that what you're saying?
Yeah, the scattering event somehow changes the state of the monopole, but if you're far from the monopole, you don't know that right away, right? So this light cone you're drawing sort of looks like, where you can be when you find out that the monopole state has changed. And because the monopole state shifts the state of everything else, because it puts you into this twisted sector, I guess somehow that's what this operator is doing. It's sort of the boundary between when you know you're in the twisted sector and when you are not.
Yeah, I think the only thing that might be I don't know how this might be, but I don't know if this is a difference in the picture, if it's somehow captured also in this other way of thinking about it. But in principle, I don't know how precise to design this experiment, but in principle, there should be some experiment that that measures the presence of an actual surface by picking up a monodromy. If I take another local, like I have this thing that is scattered up the monopole, and now I pick some local excitation that hasn't collided with the monopole at all, it's just living its best life. If I was capable of somehow picking up this monodromy, that would be evidence that there's something non-local there that acts on it, right? So so that I could just move it around. I can move this local excitation around the outgoing state without coming close to the monopole. In principle, it could be a long time after the scattering experiment has occurred, and I wouldn't have to come close to the monopole at all. But if it picked up a monodromy like this, that would indicate the presence of a surface, a non-local thing that sits at the monopole and stretches far away from it.
I think that makes sense to me. I'm a little confused about how it relates to what you said about being topological, because if it's topological, I would think there's not any specific place where I detect the surface.
Not a specific place, but going 2 pi around the endpoint, you would have to pick it up. You would have to pick up the phase, right? I mean, maybe it's not well defined to say I picked it up at the pi or I picked it up at the.
And I guess topological only applies until I actually hit some kind of charged object or something, and then stops being topological.
Yeah.
Okay.
So the
I'm not sure
endpoint
that totally cleared up my confusions, but I think I'm a little more comfortable than I was before. So thanks.
Okay, that's totally fair, and thanks for asking the question. Actually, I certainly have to think more about it. Yeah, to come up with something that's properly clear. Thank you. Ewan?
Yes, I have still a question. Can you just remind me how is the monopole, scattering monopole, and the scattering with the symmetry mass gap boundary relation? How are they related again? I think maybe you want to motivate in certain way, so there is some relation. But can you just say by words again what exactly is?
So the relation between which things, the monopole and?
Scattering with monopole, the fermion scatter with monopole, or versus the fermion scattering with the symmetry mass gap boundary.
Right. Yes.
The relationship. Remind us again.
Yeah. So the reason why these problems are connected is because when you solve this problem quantum mechanically, you see that indeed you only have one of the modes interacting with the monopole, and this mode has a correlation between well, it was here. Here. This mode has a correlation between chirality and infalling outgoing motion. So in particular, the important thing is that the solution, it's going to have it's going to reduce to a set of left movers and a set of right movers in 2D, right? And then I think what you're asking about is the boundary state in particular. Yes? Okay. Yeah. So we're assuming in 2D that the monopole boundary condition is simple. But if you had, say, zero modes on your, like fermion zero modes on your monopole, that would not necessarily be true. So in that case, I mean, we didn't write down a proof or anything that a monopole always has to give rise to a simple boundary condition like this. But in the case that it gives rise to something that's a generalization, something non-simple, yeah, then I mean this is the answer when there are no fermion zero modes on the monopole, and otherwise you would have to generalize it to a non-simple state.
Okay, but is there some picture about how the symmetry mass generation gap is just a trivial gap on the other side, right?
Yeah.
And then you have a free fermion coming in, and there are something possible, some boundary changing process which might be complicated. I'm not sure how do I describe them in terms of a shop. I guess I'm not sure this part, but I suppose there's some shop, something happened that just become SMG, symmetry mass gap. And the monopole seems to be different situation when I think you motivate that if you use the F field stress rubber around some sphere, you can detect the flux. And so I think the detail of these conditions seem different. I think I would just want to hear like a few words, a few sentences. How are they kind of think? How are the two things become related?
Okay. Maybe I can say this. So let me know if this doesn't get to the core of your problem. But so you can take a UV embedding, right? So you can take the SU2 Georgi Glashow model or something, and then now you can describe this as a nice finite energy state. The monopole is a nice finite energy state, and then from the UV theory you can integrate out these degrees of freedom. You can Higgs it, and you can integrate out these degrees of freedom, and you can it's possible to actually write down the boundary state, like the boundary condition explicitly. So then you find that a particular monopole in a particular UV theory gives rise to a certain boundary condition, right? Whereas, say I have had a different UV completion, my boundary condition might have had a different I might have had a different boundary condition.
But that boundary condition, does it imply that it become symmetry mass gap type boundary condition, or not necessary? I think I'm just trying to the symmetry mass generation. Let me shorthand abbreviate as SMG, symmetry mass generation. This mechanism, is that used in some way in the other side of the 1+1D space, that when you scatter in, is that necessary on the other side you use symmetry mass generation idea?
Maybe you can actually, I'm not sure I'm familiar enough. Could you maybe explain precisely what you mean by it's used?
So for example, the 3450 model, there's a U1 identified charge 3-fold for the left moving, 50 for right moving. There's additional one U1, you call U1 prime.
That's right.
And you can maximally preserve the U1 and U1 prime symmetry. That's a maximum 2 U1 symmetry you have. You can have a 4 U1, but you can at maximum preserve such a 2 U1, U1 prime. And finding a gap, you can even think about this non-perturbative deformation from free fermion, preserve this 2 symmetry, and along the whole process, driving from free fermion theory to a fully gap theory, fully gap symmetry in theory and without having any symmetry breaking degeneracy, without any low-lying TQFT. It's just a trivially gap, and that condition you can write down a deformation, and yeah, that's it. It's just once the theory is anomaly free within certain global symmetry, including space-time internal symmetry, that's anomaly free. There should be necessary and sufficient enough to prove such deformation exists in some way. And I'm just asking, because you're motivated in the beginning that you put this boundary condition. I wonder how serious how important that boundary condition is.
Okay. Okay, I think maybe I understand better what your question is now. So, well, the monopole setup and this 3450 model that I explained in the beginning are the same to the extent that I just take the gauge field to be background. Then I indeed find some global symmetries in 2D, and I think this setup has the same properties as what you were saying before, that I can gap it. But of course, that's not the full story, because really I'm not working with free fermions for the monopole. I'm actually in some gauge theory, and there might be corrections to the story. So I'm actually going to talk about that in a minute.
Please. Yeah, maybe
I'm not sure whether it's going to answer your question. Maybe we can do that, and then you can ask again if I'm still not answering your question. Then I'll be happy to try to do better.
No worries. Thank you very much. Thank you.
Okay, so so let's talk about the gauge fluctuations. Right, so far we've just been working at tree level, and I've been completely ignoring these gauge field fluctuations. But as I was saying, we're really in a gauge theory, and we shouldn't be completely ignoring this, because who knows, maybe it's going to modify some of the stuff that I've been saying. So let's think about the gauge field fluctuations. So it turns out that the components tangent to the S2 don't have zero modes, which just means that they encounter a barrier, so they're gapped out. Whereas the ones that are like the radial and the time components are scalars on the S2, and so they do have zero modes. Now, let's first think about QED just with a single Dirac fermion and a unit charge monopole. And then the S wave will include a single pair that's a left mover and a right mover in 2D. Then we can bosonize the 2D theory. So after integrating out the sphere, we can bosonize, and then what we obtain is a variation of a Swinger model with a space-dependent gauge coupling. So here we've bosonized these field psi and psi tilde to this phi. And the gauge field fluctuations are, they're captured by this FRT. So that's the field strength. This is a Swinger model, except for the fact that this gauge coupling here it depends on the radius. Now, if we further integrate out the gauge field, this generates a repulsive potential for the scalar. And intuitively, that means that we actually have to have the scalar vanishing mod 2 pi at r equals 0 at the origin, and not have this marginal operator theta. So usually the usual monopole boundary condition looks like this, which in the bosonic language translates to phi can have some value theta mod 2 pi at the origin. But because of this repulsive potential, it turns out that that's actually not possible once you take into account gauge dynamics. So this can also be made more precise. This is just like an intuitive explanation, but you can actually compute that the associated defect operator is irrelevant and not marginal when the gauge fluctuations are taken into account. So this theta angle is not actually there, and therefore the main effect of this small centrifugal barrier is to remove the theta angle. Now, we can also take QED with a single Dirac fermion and a higher charge monopole, and again bosonize, integrate out the gauge field, and then we obtain this action. And now the spectrum to this order in E squared contains one massive and one massless boson. But integrating out higher KK modes could in principle produce quartics as long as they're consistent with the SU2 rotational symmetry and the C2 axial symmetry. So C2 because we've taken particular values for N and F. And the coupling that's consistent with these symmetries is this one, so the cosine. And this operator is marginal. Therefore, the presence of the barrier depends crucially on this sign. And we didn't determine the sign of this operator. We've left that for future work. So whereas we can conclude in the case of a single direct fermion with a unit charge monopole that we actually get a barrier for some of the zero modes, they're lifted. For this one, we haven't determined the sign, and therefore we don't actually know precisely what happens, what is the fate of these zero modes. However, what we do know is that either sign has to lead to a non-trivial phase, and we know that because the axial C2 has an anomaly in 2D that has to be matched. That's actually all I want to say about gauge dynamics. I don't know if Euan, if that, I thought it would have relevance to your question.
Possibly. Is that the cosine term preserve certain symmetry?
Yes. So the point is just that we know that integrating at high KK modes can produce quartics. You can write down a couple of different, like you can write down all the different possibilities, but in order for that this is the only coupling that's consistent with the symmetries of the problem. So the rest aren't relevant. But basically what I'm saying is I don't really know what happens in the IR, because I don't know what the sign of this operator is. So that's the full story in the case of the monopole. Well, rather it's not.
I'm so sorry. Is what symmetry preserve that? Maybe let's see. There's at least some U1, but I'm not sure what's the meaning for that symmetry.
Oh, so right. Let's see. So the axial symmetry just shifts phi1 and phi2 by the same amount. So that doesn't do anything. And the SU2, let's see. Oh, I can't remember the sign. I can't remember right now.
But just make sure. But okay. But you are doing a QED model right now in 3+1D.
Yes. So what I'm trying to convey here is that what we've been doing is we've been just taking the approximation that there are no gauge field fluctuations. And in that case, we arrive in the same scenario as these three fermions that I was talking about before, but it's not the full story. So the full story actually has to take into account fluctuations of the gauge field. And in the simplest case, we just have one direct fermion and unit charge monopole. We can see that actually some of these zero modes are lifted. So they're gapped out. They encounter a small but non-zero barrier. And in general, we don't actually know what the answer is. That's unfortunately what I have to say about it.
And how is the side plus or minus side difficult to determine, and what makes the difference? Just to make sure I follow. You say you cannot determine.
Yeah. So I mean, I'd say in order to properly determine it, you'd actually have to integrate out the higher KK modes, and it's not impossible to do. But and I think some people might be working on it actually. So so we might know in the future. But it's just a tricky computation, and we chose to stop here. Basically.
So you're saying
it's a question for the future.
There's some net contribution from the leading order, but the KK mode contribution from higher order. You don't know which one dominant, so you don't know the sign. Okay.
Precisely.
Thank you.
Yeah. Okay. Yes. Feel free.
So I want to ask a little bit about the origin of the boundary condition. So I think you alluded to it somehow coming from the UV completion of the monopole. But if you look at the original semiton paper by Callan, it seems like the linear kind of combination that demands that you have half integer, that you get the semitons, is from the demand that all these e squared over r squared delta phi squared terms actually vanish because the energy of the fluctuation grows like 1 over r squares towards the center. So it seems like if you just read into the Callan story, the boundary condition is somehow the effective boundary condition from the abelian fluctuation rather than from the non-abelian UV completion. Do you have thoughts about that?
Yeah, I do have thoughts about it. So I think it's true that you can also find this answer in effective field theory. And the thing is, actually, for the unit charge, no, just leave it like this. For the unit charge monopole, at least you can go from the UV and you can fully derive the consistent boundary condition for a particular UV completion. But what we did actually in terms of the higher charge monopole, you can just look at the symmetries of the effective field theory and well, basically, the symmetries that you have available to you in the effective field theories determine what can come out, right? So they just like in the 3450 model, if you just make sure that the out state preserves the symmetries of the effective field theory, you will find this fractionalization.
Right. So I think using symmetry, you can definitely make a definite statement about what comes out, which is maybe the interesting part. But there's another question, which is, what is the physics effect that converts the in state to the out state? And then the question about that, it should have a crisp answer. Is it some UV physics that I averaged over, or is it the work of the abelian fluctuation around the monopole?
Yes. Well, so I would say it's the work of the UV degrees of freedom, right? Because the fluctuations, well, I would think so. The fluctuations around, so which fluctuations around the monopole are you talking about, just to be clear?
Just the AR and the AT.
Yeah.
I mean, the degree of freedom that Callan and Robokov have.
Yeah. Okay. Because the effect of those, at least for the, as I was saying in the previous slide, is to possibly create a barrier, right? And if you have this barrier, then the fermion interacts trivially with the monopole. It's just deflected. Or is there a proposal that I'm not aware of that somehow the gauge degrees of freedom are?
Well, I think that's what's in the original Robokov paper. Right?
Okay.
So
yes.
That's why it's called ABJ anomaly, right?
Yes. So I think our up-to-date, well, our take on this is it's probably different from the original statement about it, which is that it's the UV degrees of freedom that are causing this effect.
I see. All right, thank you.
Maybe I can add something quickly. So even the symmetries that are preserved by the monopole depend on the choice of boundary conditions. Like you can even have, the symmetries are depend on the choice of UV completion. You can have UV completions that do not even preserve the SUNF symmetry, for example. And so that changes the story completely. So I think everything depends like very, very sensitively on the choice of UV completion.
But if we go back to SU5, okay, then these global symmetries that you want to satisfy are just a simplified model of the 4 Cartan generators of the standard model. So then you have 4 doublets and you have 4 conditions from just charge conservation under Cartan of the standard model. So that's a fact about the standard model, not about the UV completion.
Well, the SU5 is a completion of, because if you take a U1 gauge, U1 times U1 times U1 times U1 gauge theory, and do not know that it comes from SU5, then there are more choices for what the outstate is. But if you do specify that U1 to the 4th comes from SU5, then the outstate is unique. So you can have other UV completions of U1 to the 4th that is not SU5, and that will give you different answers.
Okay, so I mean, we can continue this discussion offline, but in my opinion, the only information that comes from the UV completion is the charge assignment of the U1 monopole charges to the standard model field content. And once that's, and also like, okay, partitioning them into like doublets of SU2 monopole. But I think once that's fixed, all the information is already in the EFT. But I think this is a longer conversation that maybe we can have offline.
Yeah, I'd be very happy to continue afterwards. Also, I'm Diego, if you'd stick around, that would be great.
Sure.
Yeah. I see there's another raised hand. What's that?
Oh, yeah. So it's actually also related to a question that Offrey was asking. So you described this defects that comes out, and there's a fractional quantum Hall states on that. But in general, just by matching symmetries, you don't require that DQFT to be just U1 level n, right? It can be, there are more possible choices that are allowed by symmetries. Yeah. So yeah, so it's probably related to Offrey's question. So let's say we fix
the particular choices that are allowed is this one here, right? Is that what you're saying?
That's right. Yeah, or it can be more complicated. It doesn't need to be a minimal theories, for example.
Now I understand what you're saying. Yeah.
Yeah.
Okay.
So,
yes, please go ahead.
Yeah. But if you change the TQFT, then you definitely change the outcoming states, right? But and maybe it's related to the question that Offrey is asking, is that now if I fix the UV completion, let's say this SU2 completions, is there a way to determine which TQFT that comes out, or?
Yeah. So just to make sure that I understand your comment, it's that actually the thing that we've determined that comes out of the scattering experiment, we haven't completely determined the TQFT that lives on this surface that comes out. We've only determined its coupling to the one-form symmetry, in the sense that I could actually stack it with a TQFT that's decoupled from the one-form symmetry, right? And
that's right.
It would still satisfy all of this. Yeah.
That's right. Yeah. You basically fix the anomaly of this TQFTs, but it doesn't uniquely fix the TQFT. Yeah.
Yeah, I completely agree. So yeah, we don't have a way to figure out precisely which TQFT comes out if there's a decoupled TQFT stacked on it. So, and one idea would precisely be to pick a particular UV completion and ask this question, and then it might very well be possible to derive it directly from there, but we haven't done it yet.
I see. Yeah, that'll be very interesting. Okay,
yeah.
Thanks.
Thank you. That's actually cool, because it brings me to the conclusion. So I just want to say that we saw that the outgoing. Yes.
So Marieke, sorry for interrupting. Can I ask just so regarding Hotat's question? I mean, would that? I mean, if you have this decoupled TQFT on top of the surface, would that affect the physics in any way?
It wouldn't. So the point is, in this scattering experiment, it immediately wouldn't. Right? It's decoupled for all intents and purposes. Right. It doesn't talk to the. It doesn't talk to the bulk theory at all. So if I send in some electron again, it wouldn't be able to pick up whether or not this decoupled TQFT was there. So you would have to figure out, either you could derive it from a UV completion, or I can't imagine it, but maybe there's some other experiment you could do in the EFT that would be able to pick up this.
I see. So the idea would be that the UV degrees of freedom or something could detect the difference between the different TQFTs. This idea?
Yeah,
you cannot do it.
The idea is you might be able to write down the scattering experiment in some UV completion where you find some surface coming out, and then you can trace that down to the IR, and you'll see, okay, there is this extra decoupled sector or there isn't, right? Because I mean, I completely agree with Hotat that this is a question that needs an answer, in the sense that I throw something in, something specific has to come out. I can't just say it's up to the addition of a decoupled sector. Either it lives on the surface or it doesn't. But yeah, the idea would be maybe you could compute it in a UV completion, do the experiment fully. Yeah.
Okay, thanks.
Yeah, sure, no problem. Right, but we're actually making it to my Outlook anyway, so this works. let me just read the slide. So we saw that the outgoing states from scattering zero modes of a monopole are trailed by a topological codimension 1 surface, and that this symmetry defect supports a non-trivial topological field theory and is in general non-invertible. And there is still a question of the gauge fluctuations. We have seen that these do indeed modify some of these conclusions by lifting some of the zero modes, so creating a small barrier for the ones that we thought actually did scatter non-trivially with the monopole, but there's still an open question. So this brings me here. This is, I think, related to something, a comment that Juven had, which is we studied an infinitely heavy monopole with an internal gap. And it would be interesting to reconsider the problem, say if there are normalizable zero modes on a Tuft line, which in 2D would correspond to a non-simple boundary condition. There's also a question whether there might be a similar story for scattering in the presence of axions, where these authors also determined a non-invertible symmetry operator for the shift symmetry. Maybe there's some experiment similar experiment you can do in order to find that surface. And well, I don't even have to read this because that's precisely what Hatat said. Oh yes, and relatedly, if we did manage to find this precise topological surface in a UV completion, is there a way to excite the non-transparent anyons of the whole state? Some other experiment. And finally, one other generalization that might be like, a straightforward next step is, but interesting, then we can consider fermions of higher electric charge. Then the new feature would be that there would be an electric one-form symmetry, and it would mix in some non-trivial way with the rest of the symmetries. And the reduced theory that we would find for the gauge fluctuations would be a variant of the Swinger model, also with higher charges, and that has a whole set of new interesting features of its own. Right, and then finally we have left the question of the sign of this quartic to the future, and the final fate of the pseudo zero modes. That's it. I'd be very happy to continue the discussion.
Thank you very much. Thank you, Marieke. Thank you, bedankt. Talks to Scout to have. Thank you. Questions from people.
Yes, I see a raised hand. Yeah.
Please, Yunjin.
Hi, thank you very much for the interesting talk. So I have some question about the relation between the Chern-Simons theory in 4D. So the Chern-Simons theory in 4D setup and the topological line in 2D setup. Mm-hmm. So you motivated the Chern-Simons theory from the chiral rotation for the fermions.
Yeah.
Have you checked that if you start with the Chern-Simons theory and compactify it on the radius direction, you get the original invertible symmetry defect in 2D?
Yes, we checked that if you take this if you take the 3D TQFT and you reduce it on the sphere with the flux, then you find this invertible axial symmetry in 2D.
Is it just one copy of invertible defect or several copies of it?
Just one copy. The effect is mainly to trivialize the TQFT, which is why the non-invertibility goes away. Other than that, you just have the symmetry action on the fermions.
Oh, okay. Thank you very much.
Thank you.
Any other questions, comments?
Maybe we can discuss more informally.
Okay, so let's start recording. Let us thank